welcome. It's a big honor for me to introduce Rodrigo Bañuelos, our next speaker. I'm going to tell you a little bit about him and at the end how I met him. So Rodrigo got his PhD in 1984 from UCLA, and then he was a Bantrold Research Fellow at Caltech. Then he had an NSF postdoctoral fellowship at the University of Illinois in Urbana-Champaign, and in 1987, he became an assistant professor at Purdue, and in 1992, he was promoted to a full professor, and he has been there since then. His research, as we will hear in his talk, is in probability and applications to harmonic analysis and spectral theory. He has served in many boards, some for the AMS, so transactions and memoirs, and annals of probability. And he has also served in several committees for the AMS, the Institute for Mathematical Statistics, the Board of Trustees of IPAM, and several advisory committees at MSRI now, SL Math. He's a fellow of the AMS, the IMS, and the AWM. And he is a recipient of the NSF Presidential Young Investigator Award and of the Blackwell Tapia Prize. And in 2022, he received the AMS Award for Distinguished Public Service. And so all of these are things that you can find in his CV. I would like to also say on a personal note, Rodrigo and I worked together in bringing to life Latinx in the mathematical sciences in 2015. And then in 2018, he was one of the featured speakers, where he gave a very, very moving and inspirational speech. And this led to an interview in NPR on Latino USA by Maria Hinojosa. So if you're curious about his trajectory, he's had a truly amazing trajectory. I encourage you to go and look for the podcast. But what we're here today to do is to listen to Rodrigo, who will be talking about sharp inequalities in probability and harmonic analysis. Welcome, Rodrigo.
Thank you very much, Tatiana. It really is great to be here. And I want to thank also the AMS for inviting me to give this talk. And of course, I want to thank you for coming. Let me go on and really tell you what this talk is about. Let's see, I need to advance. Doesn't seem to. What am I? Oh, there you go. So the purpose of this talk is to discuss some inequalities on discrete singular integrals. Now, let me tell you a little bit of why I was motivated to look at these problems. So one motivation is a very old and very simple looking problem for the discrete Hilbert transform that goes back to almost 100 years by now. And the other motivation is that there has been a lot of interest in harmonic analysis in the last 20, 25 years in studying discrete analogs of harmonic analysis inequalities and results. This was initiated by work of Bourgain, Stein, Weinger, and it was followed by work of Meiger, Stein, Weinger again, UNESCO, Bourgain, Pierce, Lillian Pierce, Mirac, and many, many others. So there's a lot of activity on this subject. It's got beautiful connections to analytic number theory, which is a subject that I do not work on, so I'm not going to go at all into that direction. I first learned the basics or some of the history of these problems and the basic techniques and so on from a beautiful thesis written by Lillian Pierce, 2009 at Princeton under the direction of Ila Stein. So it's a highly recommended reading if you are beginning to study or even if you know this subject, and I guess if you know the subject, then you will know her thesis. Now, I was also motivated by this because there has been a lot of success in probabilistic ideas and techniques in applying results from probability to obtain sharp inequalities for singular integrals in Rn, on manifolds, and many other geometric settings with very remarkable constants that come up that are actually quite close to sharp. I wrote several years back, and this is an outdated article, but it's a long survey that I wrote in honor of Don Burkholder, who was at the University of Illinois, and that actually has so many interesting problems that remain unsolved even now, okay? So, you know, one thing is for certain is that the world is full of inequalities, okay? That's a complete understatement, right? We agree on that. But what we can also agree on is that we mathematicians love inequalities. We either want to prove inequalities or we want to apply inequalities, and we do this over and over and over. And you go to talks and analysis and many, many different subjects, and you see lots and lots of inequalities. So I wrote an inequality just very, very abstractly, right? So the question is, suppose that you have an inequality, okay? So somebody writes an inequality, and you look at the inequality, and there are many reasons why you will want to know that the inequality is sharp. You know, sharpness results are somehow the part of our bread and butter, right, that we do. Curiosity, you know, Euclid proved that there are infinitely many primes, right? And then, you know, well, I don't know if it was right after that, but eventually people say, if I take an integer n, about how many primes can I find between 0 and n, right? Okay, in the positive integers up to n, you know. And then came the prime number theorem, right? N divided by log n, okay? So sharp result, right? And then you can go back to the isoparametric inequality, which I will mention in a minute, okay? So there's a curiosity about getting sharp results. And sharp results often come from inequalities, right? Okay, you know, you're studying some problem, you know, and you're doing some approximations, and you want to know what is the best rate of approximations in this, for this problem, right? Okay, so they arise very, very naturally. Now, one question that comes up immediately is the inequality sharp? What is the best constant in this inequality? Okay, the next question is the equality, if the equality is sharp, what are the extremals, okay? The quantities that give you extremals, okay? Is the inequality attained, okay? Or is it always strict? And if it's strict, what do the likely extremals, right? A sequence that converges up to, gets you above, you know, 1 minus epsilon times the constant c, right? Which is the best constant. What do they look like, right? Okay, can they be fully characterized? Now, if the inequality is sharp, okay, and is attained by some class of objects, and you are looking at an object which is not in the class of extremals, right? How far is that quantity, quantity from being extremal, right? These are called deficit inequalities, and it has been a remarkable results in the last 10 years or so. For example, in one of the most beautiful, inequalities around, the isoparametric inequality, right? The isoparametric inequality says, in the simplest possible way, the simplest possible case, that if you take a region in the plane, okay, it it's got perimeter P, all right, the perimeter of the boundary, then the area of D is less than or equal to 1 over 4 pi times the perimeter of D. And this inequality holds if and only if D is a ball, right? So this is the isoparametric inequality, which is actually Quinn Dido's property, discovered by Quinn Dido after her arrival in the coast of Africa, 900 BC, right? So this is an example where all the questions have been answered, right? And I say simple, right? But you know, the question of the deficit inequality, the precise inequality of what happens if you are not at an extremal, right? If you're not the ball, and how to correct it, right? So this inequality was proved around 2008. It's a beautiful paper in the Annals of Mathematics by Fusco, Pratelli, you know, and there's a lot of people that work on this subject. And this is sort of the next level of inequalities, okay? These deficit, you know, quantitative inequalities that tell you you know, if you know the extremals and you're not an extremal, how far are you from it, right? Okay, right. Those are just examples. But here, I want to tell you a little bit of the history of the problem that I want to discuss. So a question that was around that was excited the interest of many analysts during the early part of the 20th century was the following: how does the size of a periodic function control the size of its conjugate? Right? And by a periodic function, well, let's just take a trigonometric. The question is equivalent. You know, you can just simply case take a trigonometric polynomial, and then you consider its conjugate. All right, and the conjugate is well, I can't point to it. Oh, the conjugate is also a trigonometric polynomial. I'll tell you in a minute why this is called a conjugate. And the size was supposed to be measured by the LP integral, the integrability of the polynomial, right? And you want P to be between 1 and infinity because it was already known by that time that there's no comparability that you can write using this norm, okay, for P equals 1 and P equals infinity, right? There's some other correction, some other inequalities that you can do, but not for LP. Why conjugate? Because if you take an analytic function, construct for the coefficients that the A and B, right, then you write it as a real part plus an imaginary part, right? It's two harmonic functions, right? And you see that the boundary values of U on the circle gives you the function f, the polynomial f. And for V, the conjugate gives you the conjugate function, okay? So this was the name, this is usually the name for why this is called conjugate function. Now, but you can also rewrite it, and I want to use this for a particular reason. If one of these series is P integrable, is the other also P integrable? That was really the question, with values with the P integrals comparable to each other. The case P equals 2 was very simple, is very simple, because of the orthogonality of the trigonometric polynomial. So the question was mainly, right? The real question was P between 1 and infinity. And this problem was solved by Marshall Rees in 1923. Now, here's the general formula for the conjugate function. Okay, let's see. Yeah, right. Oh, oops. Let me see if I can get myself back. How do I go back? All right. Okay. So, right. So now. Apologies for that. So the problem that Rees proved was that, of course, the conjugate function is a bounded operator from LP to LP, with some constant there that depends only on P. He actually proved that it was equivalent, although he proved it for the circle, the case that we wrote with the trigonometric polynomial. You can actually, this was equivalent to the inequality for the Hilbert transform, the classical, the most basic singular integral, right? So this integral is not convergent in the sense of absolute convergence in the sense of that we teach in calculus, but it is in the absolute value, right? But it is convergent in that you integrate away the singularity of y. Then you get a function that is h of f, and so that function exists. It exists almost everywhere. And he showed that, in fact, it's equivalent to the boundedness of this h, all right? Now, it is important to notice here that the Fourier transform of this heat curve of this Hilbert transform is I(c) divided by c, absolute value of c. So it's I times the signum of c times the Fourier transform. So if you square it again, right, if you apply it again, the square of it gets you back to the function, okay? So then David Hilbert, so here's the problem that was of interest, okay? So David Hilbert introduced the discrete operator, discrete version of this. So it's just very mundane, right? So you remove the singularity because you cannot divide by 0 now. So you remove 0 from the integers, and then you consider exact analog in the discrete setting, all right? Now, he introduced these because it was a special case. He called them the singular quadratic form. So he introduced various quadratic forms that we know, that we teach in our basic courses in analysis, and I'll give you two examples there, right? So the Hilbert, sometimes called the Hilbert integral, Hilbert's inequality, and then there's the continuous version of it, okay? So now, Rees-Bound actually, he actually proved more. He proved that the continuous version implies the discrete version, right? So he actually proved the boundedness of this discrete operator. More than that, he proved that if you let the norm, right, the norm is the best constant in this inequality, then they satisfy these inequalities. The discrete one is less than a constant times the continuous one. The continuous is less than the discrete one in the P norm, right? Now, the following year, okay, now we know precisely when Rees proved this theorem, and I put up approximately 1924. Tishmarsh, who was a student of Hardy at the time, went the other direction. So he first proved the discrete version was bounded, and then he proved that in fact they have the same norm, right? Unfortunately, the next year he wrote a correction. He said, in paragraph 4 of my paper, blah, 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 okay, this inequality, the one that he claimed, that they have the discrete one is less than the continuous one, right, with constant 1, is incorrect. And should be deleted. And then he goes on, and then he makes a little remark, which is quite important, and I'll come back to it in a bit. But the remark said that he should have better acknowledged Rees's paper. You know, he said that he was not only did he know of the result, but he knew of the technique. And what Tishmarsh did, he actually applied the technique of Rees in the discrete setting, all right? So he did not really acknowledge that in a proper way. Now, you know, it's fascinating. I love mathematics, history of mathematics. I was talking to some people yesterday about it. And it's exciting, and there's a lot of history about this problem, okay, written in an article that Mary Cartwright, so Mary Cartwright was the last student of Hardy, okay? So she wrote this article, which is called Manuscripts of Hardy, Littlewood, Marcel Rees, and Tishmarsh, and it was in the bulletin of the London Math Society in 1982. So there's Hardy, Littlewood, Rees, and Tishmarsh, okay, from left to right, okay? So let me give you a few quotes about these articles, since this is kind of you know, I take many liberties in these talks because I just don't prove too much. So here is something that Mary Cartwright wrote. I shall now try to tell you a story leading to the long letter on conjugate functions written by Rees on December 1923 and received by Hardy early in the following January. I shall quote in full because several references to Rees's work are based on this letter long before he published a full account in 1927, right? So he proved the theorem in 1923. Paper was published in 1927, right? So don't be so upset with referees, right? Okay. But actually, I'll tell you more about why he didn't publish the paper then. But in any case, so she says that these should have influenced Hardy and Littlewood and Tishmarsh. And then she writes something here. So at the end of Rees's letter, so Hardy and Rees, Hardy was in Cambridge, Rees in Stockholm, and they were exchanging letters, okay? And, you know, Mary Cartwright discovered all these letters after Hardy passed away, and then she published everything. So if you're writing letters, be careful. Somebody may publish them in the future, or maybe they'll publish all your emails now, right? Okay. So in any case, so here's what Marcel Rees wrote in June of 1923. I prove can be formulated in many other ways. The two conjugate harmonic function series are always at the same time Fourier series of functions of class LP. That is to say, if one is, the other is too. My proof has nothing to do with the Hausdorff-Young inequality, right? The extension of the Fourier transform to other LPs, which was sort of guessed that was supposed to be the technique to prove it. Now, so Rees did not answer, and so on December 18, 1923, so not the dates, 18 December, Hardy wrote back to Rees, and he says, some months ago, you said that you have proved the two conjugate harmonic functions are at the same time series of Fourier. I want the proof, italics, right? Both I and my pupil Tishmarch have tried in vain to prove it. Some attempts go close, and I feel that I could do it with sufficient determination. But if you have done it already, it is not worth us working on it, right? And he said, of course, I'll be delighted to get it published here, right? So please send me the Grand Lim de la Dame so that I can reconstruct the proof or the full proof here, right? Okay, so then 18, notice, December 18. In Stockholm now, on the 23rd of December, yeah, just a few days ago, Marcel restarts this letter, right? And he said, here are, my dear friend, here are the full proof of the theorem, right? He restates the theorem, and then he goes on to give the full proof. But before that, he makes the following he writes the following to let Hardy know how he discovered the proof. He says, the story of my proof is a very funny one. In the spring, I had to prepare an exam problem for a very poor student. That's not a very nice thing to say, but you know, it's a different topic, right? Okay, who wanted to pass his licentiate exam, an exam higher than the French license. Among the 8 problems was also the case of P equals 2. Then Rees goes on to say that he was walking home and he was thinking, my student does not know Plancherel, does not know the orthogonality of the polynomials. How is he going to discover the case P equals 2? Then he went and he discovered how to do the case P equals 2 using Cauchy's theorem, okay, on analytic functions. And then he observed that, this works for P equals 4. And then he worked for every even integer. And then he interpolated because Marcinkevich's theorem was already around, right? So if you prove from here to here, you got it in between also, right? So Hardy wrote back, and he said very many thanks. Now, when did Hardy write back? 5th of January, 23rd. And notice Marcel Rees actually finished this letter, right? Actually, he finished this letter. You know, I don't know how to go back on these things, but in any case, he finished this letter on the 29th of December. How did this letter get back from Stockholm to Cambridge? And then Hardy writes back on the 5th of January. That's a pretty interesting history there. I mean, it sounds faster than email, right? In any case, he told him how much he liked it, and he said most elegant and beautiful. Of course, P equals 4. It's amazing that none of us had seen it for P equals 4. Then he acknowledges something here because Marcel Rees had not, this happened much later in 1927 when Rees actually got a job now in Lund. And there was some exchange of letters between Hardy and Rees about the new job and so on, and there was some discussion about some acknowledgement and so on. Any case, so he went and wrote this comment. He said, I rather fear that you were dissatisfied with how Tishmarch acknowledged your work, right? And he says, T says what is essential is that theorem B is yours, capital U, Y, and it's fairly obvious that his work is based on your work, okay? Actually, he did not know some papers, so Rees did write a Cambrandu announcement in 1924 very short announcement, and that was the only thing that had been published outside of this letter that Hardy had already distributed. In any case, so then, all is well that ends well, but Hardy did acknowledge that Rees had an error, so he says there's a mistake in section, but Tishmarsh will correct it, right? So there's the correction that I read earlier. Okay, in any case, well, all right, so these are just stories, and I wasted already a lot of time, but so I'm going to now have to start and tell you some theorems, okay, so that we don't, I don't do what Hardy, if you read the mathematician's apology, you might remember his remark that the job of a mathematician is to prove theorems, okay? Not to give expository, not to be expository or comment on some other people's mathematics and so on and so forth. And he says at the very end of this remark that such activity is for second-rate minds, right? Hardy was actually full of contradictions because, of course, he was a great expositor, right, as well, according to his writing. So let me try to tell you a little bit more. So there are many, many proofs, of course, around for the inequality that you want, the discrete operator less than bounded on LP, right, with some constant. So the case P equals 2 was actually proved by Andrew Wiles in his thesis written under Hilbert, right, in 1908. In 1911, 1911, not 2011, Schur proved the case, the sharp case for P equals 2, and in fact, what he did, he invented Schur's lemma to do that. So I have the wrong day there. Okay, the case P equals 2, of course, has many, many elementary proofs, and you'll find some beautiful ones. For example, Grafakos has one, 2016, but there are many others, okay? For general P, there are also many, many proofs of these, and some very beautiful ones, more recent ones by Domelevo and Petr Mikl, and they have various papers on this subject, okay? So many proofs on these. Now, for a long time, people were trying to prove that this continuous version of the integral was P norm was equal to the discrete version, right? But without knowing what the constants were, So a lot of activity happened after Picorides in 1974 found the best constant for the Hilbert transform, which is this very strange constant tangent of 2 pi over 2p for p between 1 and 1, and otherwise they call tangent, right? And it's got a certain behavior that you can see which really verifies or coincides with the behavior in the general theory of singular integrals. Right now, let me mention here, okay, so one way to discover that or to show that is that the constant was already known for even integers, the best constant, even powers of 2, right, of powers of 2. And this was based on a very clever inequality. It was proved by Goldberg and Krupnik in 1968. And it's just induction. So you prove that inequality, and then you use a trigonometric identity that comes from high school. And then you get the inequality with the best constant for any power of 2. Burgess Davis, my colleague at Purdue, proved the version for P equals 1. So there's what is called a weak type inequality, and he found the best constant. The reason I mention that is because Burgess did what is called a conformal invariance, which is some technique that has been very powerful and is applicable in many different settings. Okay, so for example, folks who worked on SLE or many other problems, modern mathematics, these are very old theorems, right? But they continue to use it in a very effective way. And what it does, it reduces problems in analysis like these to some extremal problems about exit times, right? So there's much, so you can probably discover the constants a little bit more naturally if you do it probabilistically. But there are proofs, of course, of these Beautiful proofs, simple proofs now, right? Both analytic of both results, and probabilistic of both results. So this is nothing new here, right? So now, here is a proof of the inequality then for the discrete Hilbert transform. So we proved this with my collaborator Mateusz Kwaśniewski in Poland. And we proved that the discrete Hilbert transform is bounded, right? The constant is no more than the Picorides constant, right? Now, Ries had already proved that the Picorides constant, right, which is the norm of the Hilbert, or the continuous one, was less than the discrete one. So you put this together, and then you get the inequality. This result was also known for powers of 2, and this was done using some other quite clever inequalities which are attributed or identities, some nonlinear identities for these operators, which are attributed by Lang in 2207 to Igor. Let's see. Sorry? So the green is the norm of the discrete version. The red is the norm of the continuous version, right? So he proved, so this was the inequality that I put before. So Picorides found the value of red, right? We proved that the norm of the discrete operator is no more, right? The best constant in this inequality has to be less. So the green is the best constant in the discrete case, right, for this operator. And so what we prove is that the green is less than red, right? And Ries had already proved the other inequality. So put together, you get that, right? So now, we also proved, and this is nothing really exciting, some version of Burgess' theorem, or the weak inequality, but we are not able, and we prove again that the red is smaller than the green, right? For the continuous version is smaller than the discrete version, but we do not know how to prove the equality. So this is a nice, interesting open problem. Right? Now, I want to tell you, so I have enough time here, but in probably not very technical way, a more general kind of interesting problems that are much more challenging, I think, even than these other very, very simple problems. You see, this problem for the discrete version, okay, so, what did you learn on calculus? That sums are integrals and integrals are sums. And you think, okay, I'm just going to rearrange the sums and do blah, 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 and I should be able to prove that these two norms are the same. Okay, and well, if you're clever enough, it works in one direction, but not the other direction, okay? So, but now let's look at the general class of Calderon-Zygmunt singular integrals and their very famous paper published in 1954, right? So if you take a convolution operator, which is what they study there, with the right decays on the kernel, then you have an LP bound. That's the basic Calderon-Zygmunt theorem that we all harmonic analysis love and use, and and many applications and new applications are coming out every day, right? Now here is an added and proof in this famous paper of Calderon and Zygmunt. Here's what they say. Okay, so they consider the discrete version of the singular integral on the lattice now, right? So f, now I'm going to use f instead of sequences. So this is a function that goes from Zn to R. Quote, theorem 1 of chapter 1 leads to the following, and then they state the inequality for the discrete version, right? Okay, the discrete version also holds. Quote, for d equals 1, this remark is due to M. Ries, and the proof in the case of general D follows in similar pattern. And that's, of course, correct and true, but they did not elaborate any further, except in the case of the so-called Berling all-force transform, which is the convolution in 2 dimensions with 1 over c squared, right? So the two-dimensional version of the Hilbert transform. But they really didn't elaborate this. So here, let me look a little bit more closely at what one actually gets if you if you really sharpen all the constants and do the arguments, the full arguments, you get that the discrete the discrete singular integral is controlled by the continuous singular integral, t, in the p norm, plus a constant that depends on this beta, the regularity that comes in the kernel, and the dimension, right? And then you prove that if you take what are called homogeneous at degree 0 kernels, then the continuous version is less than the discrete version, which is, again, the theorem of Marshall-Rees, right? The generalization with a constant 1, right? So green, red less than green, right? Now, classical example that satisfies these inequalities, right, are the Rees transforms. The Rees transforms are the exact generalizations in Rn of the Hilbert transform. So look at the Fourier transform of these. I ck divided by c, absolute value, right? That's the multiplier, right? But they have another beautiful characterization, right? Namely that it is, which is what one uses when you want to prove the basic regularity of elliptic PDE, for example, that when you teach in a course from Gilbert, Trudinger, or some of these basic courses, right? That the Rees transforms are the k derivative, the Laplacian inverse of f, right? Now, if you look at that inequality and you're a probabilist, you're thinking semigroup theory and you think in stochastic processes. And I'll come back to that in a minute. But these are examples, perfect examples of the singular integrals that satisfy these two properties. So when d equals 1, of course, you get the Hilbert transform. So then you look at the discrete Calderon-Zygmunt Rees transform, right? Yeah? Now, you can study, let me just make parenthetically here, you can study, and people have studied, Rees transforms on groups. That's a different thing. They satisfy, they go with a discrete Laplacian, and they can go with random walks and so on, but not these. These are, we call them discrete Calderon-Zygmunt singular integrals, right? So you take a singular integral, you discretize it, and that's what you get. Okay, now, here's something that will come up in a minute. So the Rees transforms, the continuous Rees transforms, have exactly the same norm in all dimensions, independent of the dimension, as the Hilbert transform in 2 dimensions. It doesn't matter where you are, right? R25, Euclidean space 25, 30, whatever. It's independent. It's always a one-dimensional case, right? The controls, right? And this inequality was proved by Tadeusz Iwaniec and Gavin Martin in 1996, and we had proved it in 1995. And I like their proof. Their proof is beautiful, it's simple, it's a method of rotations, okay? To get the upper bound and to get the lower bound, you have to find close to extremals or prove some other thing, right? Okay, so there are 2 steps in proving that the norm is equal. You have to prove less than or equal to what you conjecture to be the best constant, and you have to prove that it's no better than that. So their proof is just very, very simple. Our proof uses probability, okay? And it has the advantage that it doesn't really matter whether you're on Rn, on a manifold, on a vector bundle, or many other settings. It is, if you have the right structure, then the constant is going to be independent of the geometry of the ambient space. Right? And these questions were motivated by a famous paper of Eli Stein, another famous paper of Eli Stein, in the bulletin of the AMS in 1983, with the title, Some Results in Analysis as n in Rn as n goes to infinity. And then he made various conjectures, and then people just went on and proved beautiful theorems on these, and they still are proving, okay? For maximal functions, you know, how do constants behave? Okay, Calderon-Zygmunt theory gives you exponentially growing constants in the dimension. So to get rid of all that exponentiality, you know, it's been a serious question. All right, so We proved it using probability. So the corollary of the above results, right, the comparisons from the discrete Riesz transforms and the continuous Riesz transforms, and the fact that we know it for the continuous transform tells you that the discrete Riesz transforms satisfy this inequality, right? They're bigger than P norm than NP, the norm of the one-dimensional Hilbert transform, less than NP, right? Plus a constant that depends only on the dimension, because the beta there depends only on the dimension, right? So we conjecture that, in fact, there is this extension of the inequality of Tishmarsh, okay, or the problem of Tishmarsh, that this constant actually is the same for all the Riesz transforms with independent of dimension, okay? So that when d equals 1, you reduce back to the question of the Hilbert transform. We are not able to prove that, okay? Here's what we're able to do, which I think is interesting. That for all d, we can construct a collection of operators, which we call TH of k, and we call them the probabilistic discrete Riesz transforms that are very closely related to the discrete Riesz transforms, the Calderon-Zygmunt discrete Riesz transforms, and have norms that are independent of the dimension and exactly the same as the one-dimensional Hilbert transform. Okay, and again, for the case d equals 1, this shows that. Okay, there are two things that we must do here in order to prove such a theorem. First of all, we have to construct the operators. We have to prove that the constant is no more than that, than the constant for the one-dimensional Hilbert transform. And then we have to prove that it's no less than it, right? Okay? Proving that it's less than or equal, right, is where the work comes in, and the construction comes in, and proving that it's greater than or equal is interesting, and this is why these operators are so closely related. Proving that the norm is greater than or equal, we prove that by showing that the norm is greater of these probabilistic discrete Riesz transforms, greater than the norm of the continuous Riesz transforms. So we prove the lower bound without knowing extremos for these problems. Okay? Okay. So let me elaborate a little bit on that. So where do the THs come from? They come from these inequalities, which were first proved by Burkholder in 1984, okay, that if you take two stochastic integrals on d-dimensional Brownian motion, here I'm going to take d plus 1, right? So you take a Brownian motion in Rd plus 1, and then you look at the stochastic integral. So HS is a vector and d plus 1 is a random vector, right? It's a predictable process in order for us to have stochastic integrals. And then you take a matrix, and the matrix can be so general, all right? It can be variable coefficients, it can be random, right? As long as it satisfies that the norm of it, and here I'm taking a constant coefficient matrix, is finite, okay? Then you do this transformation, so you get a new vector, AH of S, and you take the dot product, the inner product with the increments for Brownian motion, and you call these the martingale transform. And here are the basic inequalities. So the first inequality is due to Burkholder. The second inequality is an inequality that we proved with Gan Wang in 1994, that if you have an orthogonality property on this matrix, then the inequality holds with Picorides constant and is no better. Is no better, but no worse. Okay, no better, no worse. Okay, so the constant is the best constant in these inequalities. Both these inequalities are sharp. The first inequality, of course, has extensions to many different settings, and it has been used by harmonic analysts and functional analysts to study geometry, Ebonic spaces, and so on. So it's a very, very general inequality. The second inequality is very special. It requires what are called continuous time martingale. So you have to have diffusion structure somewhere on this inequality, the second inequality. But it holds very, very generally, right? So this inequality has had many applications. the Berling-Alfors operator. So there's a very famous conjecture of Tadeusz Iwaniec, okay, that was made in 1986. And these techniques actually were used to prove the best bounds known up to now. The conjecture remains open. It's a famous problem in harmonic analysis, which is related to regularity properties of quasi-conformal mappings, okay? So other kind of regularity for PDEs. The inequality holds for Fourier multipliers, you know, for vector bundles and so on. And I give some references here to some of the work that is going on this subject right now, okay? So let me tell you the difference between the continuous setting, which has been, you know, very successfully used, and the setting here that is new, okay, for these discrete problems. So the stochastic integrals, here's a picture. It's a picture of a Brownian motion. It's a picture of a Brownian motion in the upper half space of R, right? You can, what we want to do is, of course, do it in the upper half space of Rn. Okay, but this Brownian motion just runs from some point 0, comma y, and it runs from whatever point up there, and it runs until it exits the upper half space. And it can exit anywhere, and in fact, one of the connections then to integrals, expectations to integrals, is if you start this Brownian motion really, really high, namely as y goes to infinity, it exits with a distribution that is almost the Lebesgue measure. Okay, so you say, well, that's kind of strange because, you know, it's a probability, right? But okay, we'll have to make that precise, okay? So the difference now, if we want to apply it, is that we need to build a Brownian motion that will exit the lattice, the upper half space only on the lattice. And how do you do that? You also want to build the Brownian motion so that it exits the lattice and that the exit distribution is almost the uniform distribution, you know, on the lattice, right? Okay, so that you can convert expectations to, you know, little LP norms, right? Okay? And so here's what you do. You take the Poisson kernel, so it's now a little bit more technical, and you consider what is called the, well, we call it these, the periodic Poisson kernel. So these exponential sums. Now, something that comes up when you do, you know, things in the discrete setting is these exponential sums, right? Exponential sums, what I have learned, and my friends who work in number theory tell me that that's true, are much more difficult to approximate than the Fourier transforms, right? But this is one of the difficulties with this gadget. But we take this function, and we construct the following function. For every function that on the lattice, we take this function u sub f, x comma y. So now this is a function in the upper half space, which is equal to f of n times the ratios of the function of the Poisson kernel at n divided by h. And you notice this satisfies this PDE, right? And the boundary values of this function, right, on the lattice are actually given by the function f. And these are probabilities, right? So what we are constructing here is what is called a Dubh process. So now instead of taking this Brownian motion in the upper space, we take this Brownian motion which is conditioned, which has this drift that is given by this harmonic function h, which is the Poisson, the periodic Poisson kernel. And then we run it. And these distributions, right, these random variables z tau, right, the exit position of this Brownian motion, okay, is only exits on the integers. And the probability, if you start at 0, comma y, that you exit at n is given by this ratio, right? And then you consider the stochastic integrals applying Ito's formula. And, you know, if you came to Wilfred's talk, you already saw an application much more complicated than this. This is a very basic application of Ito formula. So you apply Ito's formula to this function u, right? And you look at it on the boundary values, and it gives you a representation of the function f composed with these exit random variable, z tall, right? And then you do the transformation, right? And then now you apply the Burkholder theorem, and you have the expectation of the transformation of this function is less than or equal to the 1 minus this p star minus 1, right? Times the norm of the function of the matrix times the expectation of the function. So you already prove some boundedness of some operator up in the probability space. And then if the matrix is orthogonal, then you get the second inequality, right? And now, how do you turn that into an operator? Well, you go back and you conditioned the random variable z tall to exit at the point n, right? At the integer value n. And of course, this is just a projection. It doesn't affect p-norms. It's a conditional expectation, right? So if you then apply Jensen's inequality, you have that this operator, which is now an operator really on the lattice, is bounded in LP with a very precise norm, right? And you, of course, have the distribution of the exit position of this random variable, and you have this weighted LP inequality, right? And what you want to do is just remove the end and the division by h, okay? In order for you to just get an inequality on little LP. That's what you want to do, right? Okay? So let me now focus on this last little fact, last little theorem, the theorem that we want. Turns out that as we let y go to infinity, we're going to get operators on the lattice for which you have a limit, okay? And this limit satisfies the inequalities that we want, right? So it's a large collection of singular integrals now on the lattice, okay? And they have the properties that we want. And the question is, can we strategically choose the matrix in order for us to have the connection to this T sub h case? Okay, and the answer is yes. Here's a collection of matrices that are orthogonal, and they all have norm 1. So the only thing that survives in this inequality is the p star minus 1 for the general case, and the tangent, the cotangent, the NP, right? In the general case. Independent of dimension, independent of everything, right? Okay, and so then, right, you have to, from there you can show this inequality, and then you can compute the kernels very, very explicitly, right? Okay, so for p equals 1, you get exactly the probabilistic, what we call the probabilistic discrete Hilbert transform with these kernels. For d bigger than 1, you get the Riesz transforms. And the question is, do these operators really give you anything related to what you want, right? So I have, according to these 9 minutes, I don't know whether it's correct or not, but I think I'm just about finished here. So that's the million-dollar question, and it's extremely disappointing. So you went through all of these, and you compute the kernel for this operator. Oops, okay, so now okay, so you compute the kernel for this operator, and then you know that, in fact, I don't know how to go back. Okay, so you compute the kernel. You see, this kernel is not the Hilbert transform, right? So you're very disappointed, right? In one dimension, you can compute it, but it's not the discrete Hilbert transform, right? So what is it? Right? So you prove that these operators have the same norm that you want, but you can't claim that you have solved this theorem of this problem of Tishmarsh, right, and Riesz, right? So something magic happens. And the reason why it was magic to me is that my young collaborator is a wizard at numerical calculations. And so he began to do stuff with numerical calculations, numerical approximations, and so on. And he noticed that these things look like the convolution, right? The discrete Hilbert transform look like the convolution of these new operators with a probability kernel. Okay, so then we set out to prove it, and in fact one can prove it. And it's a bit of a non-trivial exercise. One has to compute the Fourier transform of both the discrete the operator, the discrete Hilbert transform, and the new operator. The fact that one can compute the normal discrete operator is very simple. The one can compute the Fourier transform of the continuous version is a bit more complicated, but in any event, one can compute it, and then you see Jensen's inequality once again tells you that you can remove that the discrete Hilbert transform is bounded in LP by the continuous, by this probabilistic T sub h, okay? So the question is, I'm finished here. The question that we have now is this result that these operators, these discrete Riesz transforms, are related in this way to these probabilistic objects, is it true? Can one write the discrete Riesz transforms as a convolution of a probability kernel with these probabilistic operators? And the answer to that is that I don't know at this point in higher dimensions, but we certainly know it in one dimension. This is based, we have 3 papers on the subject. One is the 2019 paper. The other 2 papers are new papers. And a lot of the calculations are done in the 22 paper with Kwasniewski and my former student, Dawson Kim. And then I want to thank you because I think I am, according to these, 3 minutes and 35, whatever. Thank you very much.
So we have, thank you, Rodrigo, for a very nice talk. And I really enjoyed the history, too. We have time for one brief question, and there are microphones on the sides, and you will need to stand because from here you cannot see anything if you have a question.
Hi. Just wanted to, it may be technical, but when you use the Poisson, you call it the Poisson kernel, or I'm not sure, this exponential sum, this infinite exponential sum, can you modify that if you have not a Poisson summation formula, but what people now call crystalline measures, or Fourier quasi-crystals, or all kinds of other type of summation formulas with some coefficient, but the main point is that you have a discrete measures on both sides of the Fourier. And would that give you the same thing? Would you be able to get a Brownian motion that converges to a uniform on a different discrete set?
The answer to that is just probably yes. You know, and we are very lucky because in one dimension, right, we are able to compute that summation, right? And in fact, you're right, one uses the Poisson summation formula, right, to write it in terms of some discrete Fourier transform, right? It is, in fact, the discrete Fourier transform, right? And so I think that is correct. It should give you some harmonic function, right? Okay, by conditioning on it, some harmonic function that will make the Brownian motion, the upper space, exit at some other points and maybe in prescribed points that you may want to do. Yeah. I think that's correct. In higher dimension, and you know, whether you can compute it to do the computation, the calculations at the very end, right? I don't know. That's a good question. Thank you very much for the question.
Thank you.
Okay, so let's thank Rodrigo again for a beautiful talk.
Gracias.